Yep. Okay. So as I was saying, for the first question, it's a priority queue because you've got a queue here that we're going to be basic, people are going to be seen as close to order of arrival as possible, but sometimes, people need to cut in front. On the other hand, second question, a router needs to hold packets in a buffer and deal with them in the order they appear. That is most definitely a regular kind of queue because things are processed in the order in which they show up. If you need to model a hierarchy, then there's only one choice. It is a tree, right? With whatever's the most important is at the top, then things below it. You need a data structure to hold your previous decisions in case you need to backtrack. That is a stack. Stacks are what you use for anything where you need to backtrack. Even when you're doing recursion, you're implicitly using a stack, a runtime stack, for it to hold the method calls. All right. So let's see. The node at the top of the tree is called what? That is the root node. So there's going to be a number of fill in the blanks on the second exam where you're given a question and I'm just asking you to fill it in. Links from the nodes to a successor are called what? Well, we could call them links, but we could also call them branches, or we could call them edges. The predecessor of a node in a tree is called what? Well, beside the predecessor. That would be your parent. Your parent is your direct predecessor. I would technically accept ancestor because that is technically correct. And nodes that have the same parent are what? Well, again, a lot of what we're doing in trees for a vocabulary is where we're going to be leveraging any kind of family tree vocabulary we have. So if you've got the same parent, right? If you got A and B, what was the relationship between them? Well, they're siblings because you've got the same parent. Mind you, the relationship between A and C over here, that actually is important sometimes. Where we would say that C is the uncle or the aunt. This is important in self-balancing trees occasionally. So describe without using code how to calculate the height of a tree recursively. Okay, well, so this is where we get into a bit of a contention between the mathematics and our mathematics courses and our CS courses or CS perspectives. It really depends. First off, we need to define how are we calculating height. So I like to calculate height based off the number of nodes. So let's see. So here, if I've got the number of nodes over here, I've got 1, 2, 3 levels of nodes. So my height is 3. But in some courses, you might see that the professor likes to calculate it via the number of levels of edges you have, in which case it's 2. So what we're going to do in this case, though, so we'll just keep that in mind. So what is the height of a tree? So mind you, this tree over here, the one I just drew in this empty box, e.g. something none, that has a 0 in both cases. But this is what is the height of a tree? It is, if the node exists, it's 1 because you've got that, and then you've got a tree has its children. Right? And the height of a tree is dependent on how big its children is. So I would say that basically the height of a tree exists. The tree's height is 1 plus the bigger of the, let's go with, instead of that, let's go with, because we're talking about height, the taller of the 2 subtrees. Plus the height of. Okay, so the tree's height is 1 plus the height of the taller of the 2 subtrees, which makes sense. Otherwise, 0. And by the way, if I'm just like this and my subtrees don't exist, hey, then guess what? 0. Then my overall height is 1. All right, so draw an example of each of the following types of binary trees, using different example for each, if possible, for each tree. And again, if you have to run out for some reason, because you informed me, just, say so in chat, no worries. Okay. So you've got yourself so we want to draw different examples of a full, complete, and perfect tree. And I say different example because if you're going to be a smart aleck about it, this tree I just drew over here is technically both full, complete, and perfect. So let's go ahead and draw what the heck is it. We're going to do full, then we'll do perfect, and then we'll do complete. Okay, so what is a full tree? A full tree is a tree where I've got a bunch of nodes, right? And all the nodes have either 0 children or 2 children, right? So every single node here has either 2 children or no children. This would not be a full tree because this guy over here is breaking the rules. He has 1 child. Here, though, everybody has no children or they have 2 children. Okay, that is what a full tree is. Okay, next, let's go and scroll to a perfect tree. Perfect trees are funny because it's easier because I can just draw it and point to it and say, hey, that's a perfect tree. This is a perfect tree. And this is a perfect tree. And this is why I like that to define height the way it is. So if it's a perfect tree, I can say that that a perfect tree has 2 to the h minus 1 nodes, where h is the height. So that sounds like so in other words, if my height is 1 to the 1 minus 1, that's 1. Here I've got a height of 2, so 2 squared minus 1 is 3. And here I've got a height of 3. 8 minus 1, that's 7. So you're all. So what's great about these, so basically a perfect tree has 2 to the h minus 1, where 1 is the height, number of nodes. There's only one way that will work, and that's by drawing basically a tree of height h where all possible node positions are filled. Complete trees are less used for binary search trees and more used for heaps, as we've seen. So you've got a tree here. And a complete tree is perfect for the height of h minus 1. So this part is going to be perfect. But the bottom level is going to be filled left to right without any gaps. So this is a complete tree. Adding 1 more node over here keeps this tree complete, right? Because there's no gaps here. However, if I do this, This is not a complete tree because we've got 2 gaps over here. And for the sake of argument, right, this is a right child. We don't have any left child over here. This is not a complete tree because, hey, the left child is missing. So here we've got a gap, right? It's left to right without any gaps. So complete, not complete, 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 right? So it's the bottom level is going to be filled in left to right, whereas the top. So the reason for this is that it encodes into an array without any gaps, right? This would be index 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and so on and so forth. And you can just simply encode them into an array without any gaps. Very convenient. All right, so rather than making you draw on the exam, I will basically be giving you some questions about, hey, if I add these numbers, will it show up with as this tree? But drawing these things are still useful, so we're gonna just do this here. So draw the binary search tree that occurs after I insert each of the following. So 42. 10 is less than 42, so 10 goes to the right, sorry, to the left. Then 50 is bigger, so it goes to the right. 12 is less than 42, greater than 10, so it goes over here. 17 is greater. 80 is greater. Negative 12 is less than everything, so it goes all the way to the left. 100 is greater than everything so far, so it goes over here. 96 is greater than this, greater than this, greater than this, but less than this, so it goes over here. 105 is greater, 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 so it goes over here. And then 86 is greater, 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 less than, so it goes over here. And 72 is, I'm just checking to make sure that I didn't miss any numbers. 72 is greater, greater, less than. So adding, there's basically no ambiguity about the way it's going to turn out, ever. 196, 105, 86. Yep, okay. And so now for this other part, which is remove. And I love doing this on practice exams where I'm too lazy to come up with the LaTeX to draw that. So where I just simply say, use the previous answer and do that. So draw what happens when you remove the following: 42, 12, then 17, then 96. So we have 3 cases for removing. Okay, 3 cases. No children, 1 child, 2 child. Right? No children, 1 child, 2 child. Make sense? So no child is easy because if I'm trying to remove, so if I've got this guy and I want to try to remove this guy over here, all I have to do is just simply tell him that, hey, instead of this guy, we're just going to give you null instead. And so it just deletes. Similarly, adopting 1 child is super easy. If we want to, deleting, if we want to delete this guy, then all we do is just simply have this guy child instead be that child. We basically just tell our parent to adopt our child. 2 children is difficult in the sense that we can't really do something without altering the entire structure. So what we do is that we try our best to not alter the entire structure and then reduce it to being a problem. To being a easier problem. So what we do is that we find our next in order predecessor, copy his data over, and then delete our next in order predecessor, which is guaranteed to have one of these cases. So let's see how that in action with number with this. So 42. Let's delete 42. Well, 42 has 2 children. So what we do is we look for the next in order predecessor. What does that mean? Next in order predecessor? That means the biggest thing that is smaller than me. The biggest thing that's smaller than me. So in other words, I'm looking for the biggest thing in my left subtree. Now, the biggest thing in my left subtree is going to be the thing all the way to the right on my left subtree. So in other words, from this location, I step 1 to the left and go hard right. So 1 to the left, all the way to the right, and I find 17. So what I do then is to delete 42 is I copy 17 over here. Now I have 2 17s, but not for long. What I do is I tell this subtree, hey, delete 17 from it, which it does. And is able to do so because 17 was a no child. So next, what do I do? 12. Delete 12, that's a no child, so no worries there. Delete 17. Well, we just put that there, but okay. It has 2 children, so we need to go so we need to find the biggest thing in the left subtree. 1 to the left, all the way to the right. So we go 1 to the left, all the way to the right, which doesn't bring us anywhere. So we're at 10. So we need to delete 10. Deleting 10 is fair. So first off, let's copy 10 over to here. And now we want to delete 10 from this subtree. So how do we delete 10 from this subtree? Well, we get here, we have 1 child. To delete the child, I have my grandparent adopt the child. And then to delete 96, similar thing, I have my parent adopt the child. There we go. Wonderful, 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 wonderful. So which of the following is a preorder traversal? Well, preorder traversal is B, where we handle the root node, and then we do the entire left subtree and then the entire right subtree doing a preorder traversal of each of those. Okay. Whereas, let's see. Which of the following is a post-order traversal? Well, that would be doing the left subtree, that would be doing the root left, so it would be C. Draw the min heap that forms after inserting the following integers. So, and you can ignore the underlying array. So adding to a heap is different than adding to adding and removing to heaps are different than trees. We always need to keep this a complete, always different than binary search trees. For heaps, they're still binary trees, but they're min heaps, and they're always in the structure of a complete tree. So first we put in 8, then we put in 10, and we always insert into the position where we are going to be making sure that the item where the tree is complete. So 8 goes into the root position, then 10 goes over here because that is the next possible location. And then 50 goes over here because, again, we need to put it in a location so that it always stays a complete tree. Okay, and then how does this thing reorder? Well, we always make sure that the heaviest items sink to the bottom and the biggest items float, and the smaller items float to the top, the lighter items, so in a min heap. So 20 goes in this next location over here, then 1 goes over here. Now 1 is lighter than 10, so it's going to float up. And then 1 is lighter than 8, so they're going to swap as well. So all you do when you insert is you just simply check against your parent to see if you need a float. Okay, next we do 4. So 4 is less than, so let's go ahead and redraw that. So 4, we had 50, and then we had 4. So 50 is, 4 is lighter than 50, so 4 is going to float up and swap with 50. And then 4 is heavier than 1, so it's not going to float up as high as that. And then next we put in 3. 4 and 3 are gonna swap. And there we go. That's done. Using the heap you drew above, draw the heap after removing an element twice. Well, when we're removing from a heap and we don't really have any further instructions, we're going to be removing from the root. And the way it works for removing from the root is that we take, it always needs to remain a complete tree. So we're going to maintain that property first, and then we'll figure out how to maintain it as a heap. So to do that, we delete the root, we move the last item in the heap to the front, to the top of it, so it maintains a complete tree. And now, again, we just simply applied the property of if you're heavier, you sink, and you're lighter, you float. So 4 is lighter than 8, but heavier than 3. So 4 is going to sink and swap with 3. And again, now we've got everything being a tree. Sorry, a complete tree still, and a min heap. So now we need to delete 3. And that means that we replace it with the last item here, so 50. Okay, now 50 is pretty heavy. So we need to figure out who it's going to swap with. And so you've got, so 50 is heavier than both its children, but for it to be a max heap, we need to swap with our lightest child. So 4 will bubble up and 50 will sink down. I'm not going to do Huffman coding during the summer. I haven't really done it since we went online, but that's just simply the way what's going on right now. So now we're in the coding section, which is write a method which, given the root of a tree or subtree, computes and returns the number of nodes in the tree or subtree. You can't use the size method, forget it even exists. So to test this out, just to make sure, I'm not really even going to use the full tree class. What I'm going to be using is all I have to do to write that to test this out is I've written a private static class node that's going to hold an item, a left node and a right node, and there's just a constructor. It's just so that I can have something that I can type in an IDE that will compile. Public. There we go. Hold on one second. Okay. So public, static, void, int size, where we're going to calculate the size of a tree given the root of that tree or subtree. Stop share for a second. Okay. Now let's go back. So public static, and to do this, I'll have to have an E here. Technically, these things should be comparable, so that's what I'm going to write as well. E extends. I don't really need them to be comparable, but I'm going to go ahead and make it. Just so that I can do actual proper comparisons. Node E tree or root. So I want to calculate the size of this tree or subtree. Okay, so base cases. Always think in terms of base cases when we're trying to do this recursively. In other words, what the heck is our base case? What is the easiest thing for us to figure out? Well, if it exists, we don't know if it's got a left subtree or a right subtree, and that's just going to make it all messy. So instead, we always ask, hey, what do I do if it doesn't exist? What if root equals null? What if it doesn't exist? Also, it helps us avoid some errors. And the answer in that case is, oh, right, return 0. Because if it doesn't exist, then your size is 0. Easy solution there. Okay, what do I do otherwise? Well, I know that the size of myself is 1, right? So I'm gonna need, so whatever this, so for this, basically I'm trying to figure out, I want to know what the height the size of this tree is. So I know I'm 1, but I don't know how big these things are. And the answer is, well, I'll just have to recursively calculate it, which is to say that the int left size is equal to size of root dot left int right size is equal to size root dot right. And now return left size plus 1 plus right size. Okay. And that's going to be the size of the tree. Mind you, we can make this even shorter, of course, by just simply cutting out the middleman here, because we have all these variables that are silly. Didn't even use the myself variable. Okay, that's downstairs. Okay, and there we go. That is our the size of our tree. Okay. Okay, there we go. So that is our first one. You can, again, ignore this one. This was from yesterday, from the review for the final exam I was doing for a different class. So next question. Write a method which, given a tree, returns whether or not the tree is a full tree. This is slightly different than the recursive traversal methods we've tried so far. Well, because we've got interesting questions about how do we figure out if something is full or not. So, and because we actually do care about our children before we do recursion. So public static Boolean is full, and we give it the root. So first off, if I don't exist, that means I'm an empty tree. So an empty tree, technically every node has 0 children or no children, so I'm going to say return true. Also, I'm going to go ahead and return true, and just right here until I get until otherwise I need to otherwise change it, just so I can compile. So first off, if the root is null, then that's a base case. Easy base case is a full tree. So what's another way I can figure out whether or not this sound effects downstairs? What's another easy way I can figure out whether or not this tree is going to be full? Well, I can check without necessarily looking into the contents or anything too much if the left subtree and the right subtree actually exist. So for instance, if root dot left is null and root dot right is null, so if I'm a tree, and then if I'm the root of a tree or subtree, and I look at my left node and my right node, and I notice they don't exist, hey, I know I'm full because I know I'm a node that has no children. Likewise, if I look at this and say, hey, I have a left subtree, but not a right, or I have a right, but not a left, in that case, return false, because I have one child when I should have a 0 or 2. Otherwise, I have 2 children, in which case I can be outside the if statement now. I have 2 children, and that means that I have to use recursion, which actually is fairly easy to do. What I'll do is just simply say, well, I exist, my children exist. The only way I can know if I'm full is that if my children are full as well. So is full root dot left and is full root dot right. And that will ask, hey, is my left tree full? Does every node in there satisfy the is full condition? And the answer is yes. If the answer is yes, I'll check my right subtree. And if they're both true, I'll return true. Okay. Let's look at another one. Equals. This one was extra practice because it was extra hard. Return whether or not the concept of the tree are identical. Do tree A and tree B store the exact same data in the exact same way? So this one's not too bad again. Also a Boolean method. But here's the thing that would throw most students off on an exam, which is the fact that I've got basically a root, I've got basically an A and a node E, B. I'm going to go ahead and basically say return false. Actually, and let's give them a good name to root A and root B. All right, so I'm going to assume false until proven otherwise. So first off, we can check if they're equal first off by checking combinations of them being null. So if root A, so basically we got to make sure that they've got the exact same structure in the exact same way. That seems like a hard problem for right now. So let's focus on the easy stuff. That's the power of recursion, allows us to focus on the easy stuff first, which is, well, okay, let's just assume like the simple cases here. What are the simple cases? I get past nothing. I get past one node. I get past the other node, but not the other. And then I get past 2 nodes. Now, in this case, it doesn't matter what subtrees there are because they wouldn't be equal. Same over here. They wouldn't be equal. Right? Doesn't matter. There's no way they can be equal in structure in those cases. Now, over here, on the other hand, you know, they're both blank, so they're equal. Great. So we've got 3 base cases that are easy to deal with over here. And then over here, we'll reserve what we need for that one. So if root A is null and root B is null, so if they don't both exist, guess what? They're equal. Awesome. That's super easy. Return true. Otherwise, let's go ahead and copy this a 2 more times. So if the left subtree exists, but the right subtree, sorry, if A exists, but B doesn't, they can't be equal. You got something and nothing, and something does not equal nothing. Similarly, if we've got nothing and something, nothing doesn't equal something. So we're going to go ahead and return false for those. Okay, now we have one more case where we can say, okay, well, they both exist. So what about, so now let's check their items against each other, because we want to make sure, because before we bother checking about like this thing about the structure anyway, we got to check, hey, do these items exist? They have to have the same items in the same location. So if I'm doing 2 subtrees, I'm assuming that basically that these are both the root of the subtree or the roots of the subtrees. So we check them. So do those 2 things equal? So if they do not equal, that's an easier thing to make a decision about. If they don't equal, return false. Otherwise, they equal, which means we got to figure, which means great. So we're in this condition over here, which says, okay, so if they're both equal, then we've got this root A, we've got B over here, and they both have these subtrees, and we know that these the two root nodes match. Okay, so how do we check to make sure that the left subtree and the right subtree, oh, and I should probably rename this because I have called it is full. That's what I get for copy pasting really quickly and talking really quickly. Right, you have this. So this entire structure over here, and we need to check if the structure are the same. Well, really all we need to do is actually just check, hey, is this subtree equal to this subtree? And is this subtree equal to this subtree? And let the recursion handle it, because it does. Which is, so we'll return equals. We want to check two things. First off, do the two left nodes equal each other? So we check, hey, are the left nodes and the right nodes? So how in the world does this just solve all of our problems? Well, the answer is that if my subtrees are the same, then awesome. No matter that makes sense. If they're the same, it's going to return true. So because it's set up to return true if everything's the same. So where's it going to fail? Are they going to break? So basically, if they're both blank, will return true. If we have one that has a left subtree but doesn't have a right subtree, it will return false. And if their items don't match, they'll return false. And if the structure is different, one is essentially going to have something where the other is not, so it will return false, or it's going to have a zig where something else zagged, which will cause a blank, which will make it return false. So this is all you need for the equals. Notice that a lot of this was just figuring out the base cases and then saying, oh, we've got two things to compare to. We've got a left side and a right side to compare to each other, so I need to make two calls there. So here's one that is not a tree method. It is a map method. Write a method which returns what characters occur in a string and how many times each occurs. So this is one of those, until you learn maps, is almost impossible. I say almost because you can do some clever things with arrays and associate each index with a character. But that's just making a map with extra steps. Well, actually, technically making the map without the extra steps that make a map, but so a map makes this much easier to do. What we're going to do here is we're going to iterate through the string and figure out which and we're going to basically make a frequency count of each of these letters. This is something that's very difficult with what we've had so far, because essentially there's not really an easy way to organize it unless you impose order yourself, unless you use maps. Okay, so what we're going to do over here is that we're going to just steal this and give this our output. So map is equal to new hash map. I'm the map, I'm the map, I'm the map. So return map at the end. So now we just need a populator. So what we need to do is that we need to go through this word and count each time and look at each letter and count the occurrences of each letter. So I'm going to use a for each loop. Now, very inconvenient in Java, in my opinion. For every car letter in our word, you can't do this in Java. You can do it in Python. For each character in word, you can just simply say for letter in word. Boom, done. Python. But this is one of those stupid things about Java where it doesn't have an iterator for a string. So what we have to do instead is do word.toCharacter array to turn it into an array, and you can iterate over an array using a for each loop. It's really silly, but whatever. So now, I could have done the same thing with the char@ method, and it would just taken me just a bit more clicky-clacky typing. But okay, so for every character letter in the word character array, what are we going to do? Well, I want to know if I've seen the character before. That's what it comes down to with the map. The main question is, have I seen this character before? So if not map.contains key letter, if it doesn't have this letter, very simple. Map.put letter 1. So what this does, it says, hey, is this a key yet? Is the letter a key yet? Is it inside the map yet? And I say, yeah, I haven't seen it yet. Well, I say, well, we've seen it now, so we're going to put the letter in, and then we're going to put in 1 because we've just seen it once. That's the time we've seen it, once. Otherwise, so this is if I haven't seen it before, if I haven't already put it in. Otherwise, I put it in, it already exists. So what I'm going to do is I'm going to say, hey, get the number of times it occurs previously. Map.get letter int prev sightings is equal to, so the number of times I've seen it previously is equal to just simply retrieving the number of times I've seen it before, be it 1 or 2 or 5 or whatever. And then what I do is I say map.put, which will update this letter, and then prev sightings +1. Make sense to everybody? This is actually fairly straightforward because we're using a map. Very common thing to do where we're counting with maps. Maps, again, are used for kind of 3 different things, which is a database kind of retrieval lookup key value pair. So given like a customer's email address, look up all the information about the customer. That's the key value pairing there. The other thing is what we see commonly on exams are frequency counts, where given something to count, but we don't know how many different things we want to count them. So I'm able to count the number of A's appear, or a very common one is given a document, figure out what the most common words in the document are. Well, you can't really do that with an array because you have to keep track of, if you want to find the most frequent one, you have to keep track of all the numbers, all the items you've seen. So, and then figure that out at the end. So what we do here is that we just simply have the key being the thing and the value being the number of times I've seen it. And then finally, what we have here, what we have for the big homework, probably the most difficult homework in this class, which is the cheater's hangman, we have the key is equal to a category, and the value is all the things that are in that category. But on our exam, we're focused on the frequency count, which means, hey, for all the things here, so for all the things in this, count the amount of times each occurs. So, and the way that works is that if I've not seen it before, well, now I've seen it once. So register that with say I've seen this key once. Otherwise, get the number of times I've seen it before, and seen it once now, I've seen it once more time, so I add 1 to that value. Now we can shorten this up quite a bit. First thing we could do to shorten this up is say, hey, rather than using the previous sightings, we just simply nest these calls. Nothing wrong with that. Java also has a super useful method as well called map.get or default, which says, hey, I'd like the letter 0. So what this does is says, if this is in there, I'd like the key, please. Right? If this is in there, if this key is in there, I'd like the value associated with it. So if I've seen the letter E 5 times, give me 5 back. But the default value says, hey, if you don't have anything in there, if you haven't seen it yet, give me a 0 instead. So I could do something like this. Int prev for prev sightings is equal to this. And then map.put letter prev plus 1, which, just like we did over here, is that we can further shorten this and thus basically have just one item and one thing in our loop, which is if we've seen it before, give me that value, otherwise give me a 0, and now we put in that value plus whatever we got plus 1. Okay. I'm going to skip this because I don't really think it's necessary. So what are collisions in hash tables? Why do they occur, and how are they handled? So analysis here. So hash tables are the backbones of maps, and the idea here is that with hash tables, we can get constant lookup time by basically saying that every possible key has an index that we can map it to. We can figure it, and we can just simply say, hey, given this key, I'm going to hash it, and it's going to give me an index, and I can just go to that index in constant time. So it's very powerful because it gives us constant time lookup for anything, except the fact that we're saying we can take any key and turn it into an index. But any key is an infinite kind of possibilities, right? There's an infinite there. If our key is strings, there's infinite possibilities of strings, thanks to these infinite number of monkeys typing on infinite number of keyboards. On the other hand, we have a finite amount of array because I don't have an infinite number of memory. So what we do is that we use this hash function to basically translate those two things, to turn a key. We take a key, and that will turn it into an index. But because we have an infinite amount of key and a finite amount of index, so because we have an infinite amount of keys and a finite amount of index, you're going to get a collision where two keys try to occupy the same space. So what are collisions? It's when two keys try to go to the same index. Why do they occur? Because there's an infinite number of keys and a finite number of indices. How do we handle them? How do we resolve them? So we learned two broad methods in class, which is open addressing. And then the other method we've learned was chaining. Now, there's actually a lot of different ways to resolve them. There's ways like cuckoo hashing, which is that if I'm adding an item and that item spot is taken, it's going to kick out that item and force that item to look for a new spot. That's one way to do it. But then there's open addressing and chaining. Open addressing is fairly straightforward. It says, if my spot is taken, I'm going to look for the next available spot. Now, there's two methods we learned as to how we define next. So linear probing defines next as what is the literal next available space. So if I've got this array over here, right, I'm trying to get into this spot, and it's taken, I'm going to look at this spot first, then this spot next, then this spot until I find an empty spot that I can take. Okay. On the other hand, quadratic probing, we also learned that there's something called quadratic probing. The disadvantage with linear probing is that if we get unlucky with our inserts, we can get nice big clumps. So what we do with quadratic probing is that we say, okay, we're going to say the next available spot is defined by, I'm going to look 1 squared away, then 2 squared away, then 3 squared away, then 4 squared. So I'm going to look. So if I can't take this spot, I'm going to take 1 squared away, which is this. If I can't take that, I'm going to look 2 squared away from our original spot, which is 1, 2, 3, 4. So I'm going to try looking over here. And if I can't take that, I'm going to try looking 9 away, which leads to less clumping. So open addressing simply resolves it by looking for the next available spot, where next is defined by either the literal next available or by progressively looking at further and further distances. Chaining, on the other hand, basically says, hey, collisions are no problem because collisions occur because multiple things can't occupy the same space. And so chaining says, well, let's just make it so that multiple things can occupy the same space by basically having every space be a linked list. Every space is instead a linked list that has multiple items, that can hold multiple items. And so what you do instead is that you simply, if you insert something, you just simply add, and it's your spot is taken, you just add it to the end of a linked list. So chaining just simply means every spot is a linked list. Collisions are handled by there being a linked list. And again, in the lectures, I go into detail as to why this is still constant time, even though linked lists are normally O of n. But the answer is because of the way we eventually have to redistribute it. On average, we can maintain constant time by having by keeping the average length of the list to a small number. All right. So what is the runtime, worst case runtime of insertion and deletion in a binary search tree, and why? So our average runtime for binary search trees is log base 2, but the 2 here is implied, of n. That is the average runtime. And this occurs when the tree is balanced, where basically that means that if I've got a node here, then, and I've got two, and this node has 2 subtrees, if it's balanced, then approximately 50% is going to be in the left subtree, and about 50% of the remaining nodes are going to be in the right subtree. So that if I'm searching for an item or searching for a place to insert and I choose going left or right, that means that it's going to be that means that I can essentially eliminate half the search space with the by going to left or right. Just like the binary search algorithm. So on the other hand, what is the worst case runtime? Well, the worst case runtime is actually O of n unless it's self-balancing, and let's see why with a very common sentence. So the quick. So let's add the quick brown fox jumps over the lazy dog to a tree. So the becomes the root, quick, q becomes before t, brown comes before both of those. Brown, fox comes comes before, after brown, fox, jumps, F, G, H, I, J, jumps over the, already occurs, so we're going to ignore it. Lazy, J, L, so because L comes after J, but before O. And then dog. Dog comes before this, comes after this, before this. So there we go. Okay, So this is a highly unbalanced tree, even though I just kind of took a real common sentence from the English language. Okay, and so this is unbalanced. Well, why? Because every time I go, say I'm trying to find out whether the word cat exists in this tree. Okay, I'm going to go to the left. So cat comes before the. So if the cat is in here, I'm going to go to the left. It's going to be to the left. Same with quick. If cat comes before quick, so it's less than. So we're going to go to the left. But cat comes after brown. So if it before brown. So if it the cat comes before the, so it's going to go to the left. Cat comes before quick, so it's going to go to the left. Cat comes after brown, so we're going to go to the right. Cat comes before fox, so we're going to go to the left. Cat comes before dog, so we're going to go to the left. And so we don't see a cat, so we're done. So what was so bad about that? Well, every time I moved, I was only eliminating a single node from my search space, which was the node I was on, rather than eliminating half. This is essentially a linked list with extra steps. Or let's just go ahead and assume I add the numbers 1, 2, 3, 4 all the way up to a binary search tree. Sorry, so 1, 2, 3, 4, 5. So what is the worst case runtime for insertion and deletion? O(n), and the reason is because if our tree is unbalanced, we just basically create a linked list with extra steps, where moving when we're searching for something, we're just eliminating one item at a time rather than half the tree. Now, the way binary search trees work is that they always are balanced at the end of every operation. And if we add something or remove something from a self-balancing tree, what's going to happen is that the self-balancing tree will say, this made me unbalanced. If it makes it unbalanced, the tree will detect that and say, this made me unbalanced, so let me rebalance. So, and how long does that take? Well, adding and removing, again, takes log n time, and then rebalancing takes log n time. So you got 2 log n, so it's not too bad. Okay. So that is the review for the second exam. I'm going to go ahead and since it's 10:50, let's take a 15-minute break because we're supposed to have a break between our quote unquote lecture and our lab section. So I will be back in about 15.